So what I'm going to do is talk about statistics and teach you statistics today, the basis of the general linear model, which is what a lot of our statistical analyses are based off of. So we have the GLM, the general linear model of statistics. A model is simply a representation of reality, just like an architectural model is a representation of a house that's going to be built, or a rocket model, like what you saw with like the Saturn V. It represents reality. This is a numerical statistical representation of real world patterns. That's the model part. So what is the linear part? The linear part means that there is a linear association between variables, meaning a literal line that we can look at. So if we have an X variable and a Y variable, say this is hours of sleep, so we could say sleep and cognition. So maybe we could say as sleep, hours of sleep at night increase, and scores on cognitive tests also increase. Then we have a positive line, like relationship between these, that can be represented linearly. Now this is the best fit line, meaning your actual data points could be like here, here, here. So they're not going to be directly on the line. It's called a line of best fit, meaning it's the slope of the line best reduces the error. So what's the error? It's the distance from the line, this distance. Now, the line can also be in the opposite direction, right? So that would be as X increases, Y decreases. And so that's sort of a negative pattern. So why is the general linear model so popular in statistics? It's because we can take each variable and look at its distinct association with our dependent variable in a univariate system. A univariate system means that there is one dependent variable, or y, right? So there's one. So we can look at, this is one of our independent variables, x1. We have another one, x2. x3 is another independent variable. And then we have our intercept or mean, and then our error, what I talked about, that distance from the line. All of these things together influence y. And in the general linear model, it allows us to take each of these and use them separately to predict y. We can parse these out, these separate independent variables, and look at their effect on y. Algebraically, that looks like this. So we've got y is equal to the intercept plus the sum of our x variables. So that would be like b I x I plus our error, or if we're going to remove the error, which we often do, then the equation algebraically then becomes y prime, which is our predicted y based on x, is going to look like, it's the formula will then look like this. So now we have no error. We've taken the error out. Essentially, this is the fundamental algebraic equation for the general linear model. So when I'm talking about separating the x's and looking at their individual effects on y, what that means is you can literally partition all the scores into separate components and look at them. So if we're looking at just separating a y score, just a raw y score, it would be y is equal to the mean plus y prime, the predicted y, minus the mean of y, plus our error. So our raw y score, so this is for raw scores, minus our predicted y. So that's a raw score. If we want to, all these add up, they're additive in the general linear model. Now, if we want to look at the effect now of x's, right? We want to partition in a regression. A regression is that line, right? So if we want to look specifically at x variables and understand how they impact our dependent variable, we can partition those as well. So what that looks like, if we're going to do what's called a bivariate regression, that means we are taking one x and one y, like here, and we're predicting y values based on x. But what we have is we have raw scores. So say this is 2, 4, 6, 8, and this is like 4, 10, 14, and 20 or something like that, right? So we have our raw scores here. But we want to know our predicted general score. So like we want to know for every increase 1 unit in x, on average, how much does y increase? So this raw score doesn't tell us much. We want to know the average of the increase in y. So how do we understand that? We have to partition the scores. So in order to do that, we want to know, so we're going to go with y, our predicted y, minus my squared, though, plus our raw y minus predicted y, the sum of these. This is called the sum of squares. So what that is the SS regression. So the sum of x's effect on y of what the explained variance, so this is variance explained, and then y minus y prime is our variance unexplained. So no sample is ever going to perfectly match the population. It's never going to perfectly predict. You're not going to have perfect dots like this on a line. They're always going to be slightly off. So this is looking at the regression. So if you got the mean, say right here. So you've got one that's got to look at, you've got to look at where is the mark from the mean to the regression line, and then from the line to the actual point. This is variance explained. And this is error right here. We don't know why that occurs. So we're subtracting our raw y from our predicted y to do that, to figure out that unexplained. Now this is a bivariate regression, meaning there's only one x and one y. But in research, we often want to combine more than one y. But also, one of the things we want to do in regression as well is we want to, in order to get those predicted values, so y prime is our predicted value. How do we get that predicted value? Well, the first thing you have to do is know that in order to get a predicted y score based off of x, so that average that we want of unit change, is we have to find what the equation of this line is. So this is how we discover the best fit line to begin with. So you've probably heard of slope, right? So that shows how steep the line is, and it also shows what direction it's going in. Is it going positive or is it going negative? And how steep is that line? So in order to find the y value, you have to solve for the slope first. So when we've got a data set, then what you're going to do is look at, so the slope is equal to the sum of cross products over the sum of squares x. So sum of cross products, so if you've got, say, x, y, then you're going to look at sorry, I'm just getting this all out here. Wow, that's really, really bad. Okay, so what we have to do in our data set in order to find the slope, I'm going to make this smaller so you can understand what this is. So this is our raw numbers that we may have gotten from our participants, right? You're going to find the mean for X, you're going to find the mean for Y, then you're going to subtract the raw X from the mean, and then you're going to square whatever that value is. That squared value is the sum of squares X, and you're going to do the same thing for Y, that's the sum of squares Y, and then you're going to have the sum of cross products, which is X minus mx times y minus my. So that then you're looking at both x and y together and timesing those differences, which gets you this top number, and this gets you the denominator. So that's how you're going to find your slope. And so whatever that value is, you're going to be able to put the slope in there. So say it's positive 1.2, right? I just realized I put mx in there. It's actually just bx. I don't know why I did that. Because to find your predicted values, you're gonna put your x's, your raw scores here. So your raw y scores. And then this right here, the intercept, to find the intercept, you have to find the slope first, because the intercept to get that number, that value, that is my minus bmx. See, I did the formula for solving for the intercept by accident. So then you're going to take the mean of y, which is this. You're going to input it here. So say if it's 5, you put it here. And then now we've solved for the slope, so we can solve for the intercept. B is the intercept. So then that would equal, A is equal to 5 minus 1.2 times whatever our x's mean was. Say it was, I don't know, 6. So then when you solve for that, you have your intercept. I'm just gonna sort of make up a value. I don't know. I don't know. Anyway, so then you're able to put all of these y's in there. So then you can solve for 6 and go down the line of raw scores. Now there's an x there, but that's not this, because we're interested in the predicted value of y, right? Now that is for one predictor of x. We have something called a multiple regression, which is multiple x's, And that formula is equal to A plus B1x1 plus B2x2 plus B3x3. Say we have 3x independent, we have 3 independent variables and we were wanting to look at those effects. Say on cognition, say we've got hours of sleep, coffee drank that morning, cups of coffee drank that morning, and I don't know, commute time to the testing location. I'm totally just making that up right now. So we want to look at all of those things on the effect of Y, which is cognitive score, right? So that's what this looks like. Now, if we didn't have predicted, we would add the error there, but I've subtracted that out because that's what we do. So here we have what's called a multiple regression. It's too difficult to calculate out, but the principle is sort of the same. However, each x is going to potentially correlate with the other x's. And so what happens is you want to know the individual slopes, and you don't want to know how the x's are all correlated, but you want the value of those slopes given the fact that they're going to be weighted with the correlation with the y variable of these other x's. So there's something called sweeping that is done. So say you have like x1, x2, x3, and then it affects x1, x2, and x3, and you're going to have all these values where it affects each other. Well, what you just want in the end is B1, B2, B3, and then error. So you want to get rid of, you don't want to know how all of these x's correlate with each other. You just want to understand the weighted value of each slope, because you have to take into account each variable is going to affect the other. But we don't want to know all the separate effects. We want to know the weighted effect to the weighted slope. This sequential removing of the variance of all these and correlations of all these x's is called sweeping. I can't do that mathematically on here. It would take far too long. You do all of multiple regression through computers now. I don't know how they did that back in the day.